Before moving on, we need to have a really good grasp of how Git works internally. So I've made another experiment. I create another file, readme2.markdown, with the very same content of the first file. So these are these two files with the same content. If I'm going to do another git hash object with a new file, and I ask Git to write this new file content to the internal database, I've got the very same file name of the previous file. That's because I have two files with identical content, and since Git Internal database does not anything else than taking the content of a file, taking a stream of bytes, and put an header, compress and create a file with the name calculated by the hash of the content of the file, this implies that if I have two files with the very same content and I ask Git to save the content of the file into internal database, I will have the same result file. If you want to explore a little bit more what's inside the file, I've created a small and stupid program written in TypeScript that is capable of taking a file in the Git database and extract the content to some other file. So I have this command. It's a utility of mine. You have a help, and I can point the utility to the right files into the Git internal database. I ask to the operation inflate, and I ask to put the output file in this new file. So basically, I can copy this file. I'm asking to my utility to get the files taken from the Git internal database and expand to see what's really inside the file. And I can now open a file, and I can go to file system, tmp, inflated, and Visual Studio Code tells me that the editor is the file is someone binary, but I can open with the text editor standard because I want to show you that the file is nothing else than a header, and the header will identify in Git that this file, this binary file contains a blob, so it contains a stream of byte. Basically, it's the compressed version of a file. Then I have the length of the original file, followed by a null character at 0, and then the original content of the file. So you can see that the original content it's here. This confirms us that Git does nothing else than taking a stream of byte, calculating the length, creating a header with blob space length of the file. Then it put a null character at 0, and then followed by the stream of byte. When Git created this blob, it calculate the hash, the SHA1 of this binary, the resulting binary blob, and then it used this hash to write the file on internal database. So this will confirm us that Git is doing nothing else than taking a file, binary stream, taking the length, prepending a header, and calculating the hash and writing to the internal database. If we come back to the original repository, we can use another internal Git commands to show the content of a blob file inside internal Git database. So if I can use git cat file -t type as an example, and I'm asking Git to give me, oops, it copied too much data. Give me the type of the object stored inside this ID, and it tells me that it's a blob, and I know that it's a blob because I've compressed the file, and I can use git cat file.p, and as you can see, this will cut me the original content of the file, so I don't need to resort to some custom written utility if I want to examine what's inside an internal database object in Git. So I can take every object inside the database, use cat file-t to understand which kind of object is stored inside that entry, or I can use cat file-p to print the content of that entry. As a final example, I don't need to specify the whole content of the whole SHA1 identity of the object, because I can use 6 characters or more, depending if the first 6 characters are enough to automatically identify one single commit. So if I'm asking to cat file -p AD0E41, if there's no other internal object that starts with these 6 characters, it is going to work without any problem. As a final proof, I've come back into the directory where I have my basic file operation TypeScript file, and I can create a new operation that this time it's called hash. So I'm going to create with TypeScript the very same operation that Git is doing when it compresses a file. So I take the readme2 markdown, this new file that was created onto the original folder. I've modified the file so it contains hello Git2 to create a new blob object, and I'm calling my utility in TypeScript, telling to write the result of the object in tmp directory. And it tells me that it created a file with this hash. So the output is very similar to Git hash object, as you can see. And it's entirely written in TypeScript. You can see how it works, but basically it simply does what hash file do. Take the content of the file, prepend a header, and then calculate the hash and compress. Now I can go to my tmp folder and I see that indeed it contains that file. I'm not going to open, and I'm going to do an operation that you should never do in real life. I'm inside the Git, the .git internal Git database, and I can create a new folder. Remember, the first 2 characters of the folder should be the first 2 characters of the blob, the SHA1, so EC, and I create, and I'm going inside the EC, and I'm going to take this file and move to this directory. And then you should remember that the first 2 letters of the file should be removed because they are part of the directory. So I rename the file, and if I'm going back to my original repository, I now have another piece of object binary inside the database of Git, but this time I've created this object with a TypeScript solution made of mine. So it's my custom code, and it shows you that Git is doing nothing special. And as you can see, I've already tested this, but I can show you another time. I use the git cat file -p to print the content of the EC6F62 file, and indeed Git find that it is a valid Git object. So Git basic work is really simple, and I have demonstrated you writing a simple TypeScript file with 789 lines of code that can basically extract and compress a Git, an object in the same format as Git uses internally.